Behind every breakthrough is a simple idea, and artificial intelligence for sustainable applications reveals the ones that matter. We will focus on what it says about data and image. Stay with me, the best part is near the end. Chapter 1: Medical Applications. Predictive models of Alzheimer's disease using machine learning algorithms and analysis. Introduction: prediction of diseases using machine learning materials and methods. ML algorithm and their results. Support vector machine, SVM, logistic regression. K-nearest neighbor algorithm, KNN, naive Bayes finding the best algorithm using experimenter. Application conclusion. Future scope. References: 2 bounding box region-based segmentation of COVID-19 X-ray images by thresholding and clustering. Introduction. Literature review. Dataset used. Proposed method. Experimental analysis. Conclusion. References: 3 steering angle prediction for autonomous vehicles using deep learning model with optimized hyperparameters. Introduction. Literature review. Methodology. Experiment and results. Conclusion. References: 4 review of classification and feature selection methods for genome-wide association SNP for breast cancer. Introduction. Literature analysis. Comparison analysis. Issues of the existing works. Experimental results. Conclusion and future work. References: 5 COVID-19 data analysis using the trend check data analysis approaches. Introduction. Literature survey COVID-19 data segregation analysis using the trend check approaches. Results and discussion. Conclusion. References: 6 analyzing statewise COVID-19 lockdowns using support vector regression. Introduction. Background proposed work. Experimental results. Discussion and conclusion. References: 7a systematic review for medical data fusion over wireless multimedia sensor networks. Introduction. Literature survey based on brain tumor detection methods. Literature survey based on WMSN. Literature survey based on data fusion. Conclusions. References. Chapter 2: Data Analytics Applications. An experimental comparison on machine learning ensemble stacking-based air quality prediction system. Introduction. Related work. Proposed architecture for air quality prediction system. Results and discussion. Conclusion. References: 9 An enhanced k-means algorithm for large data clustering in social media networks. Introduction. Related work. K-means algorithm. Data partitioning. Experimental results. Conclusion. Acknowledgements. References: 10 An analysis on detection and visualization of code smells. Introduction. Literature survey code smells. Comparative analysis. Conclusion. References: 11 Leveraging classification through AutoML and microservices. Introduction. Related work. Observations. Conceptual architecture. Analysis of results and discussion. References. Chapter 3: E-learning applications. Virtual teaching activity monitor. Introduction. Related works. Methodology. Results and discussion. Conclusions. References: 13 AI-based development of student e-learning framework. Introduction. Objective literature survey. Proposed student e-learning framework system architecture working module. Description. Conclusion. Future enhancements. References. Chapter 4: Networks Application. Comparison of selective machine learning algorithms for anomaly detection in wireless sensor networks. Introduction. Anomaly detection in WSN. Summary of anomaly detections techniques using machine learning algorithms. Experimental results and challenges of machine learning approaches. Performance evaluation. Conclusion. References: 15 Unique and random key generation using deep convolutional neural network and genetic algorithm for secure data communication over wireless network. Introduction. Literature survey. Proposed work. Genetic algorithm, GA. Conclusion. References. Chapter 5: Automotive Applications. Review of non-recurrent neural networks for state of charge estimation of batteries of electric vehicles. Introduction. Battery state of charge prediction using non-recurrent neural networks. Evaluation of charge prediction techniques. Conclusion. References: 17 Driver drowsiness detection system. Introduction. Literature survey components and methodology. Conclusion. References. Chapter 6: Security Applications. An extensive study to devise a smart solution for healthcare IoT security using deep learning. Introduction. Related literature. Proposed model conclusions and future works. References. 19a Research on lattice-based homomorphic encryption schemes. Introduction. Overview of lattice-based HE applications of lattice HE NTRU scheme. GGH signature scheme. Related work. Conclusion. References. 20 Biometrics with blockchain, a better secure solution for template protection. Introduction. Blockchain technology. Biometric architecture. Blockchain in biometrics. Conclusion. References. Index, also of interest. End user license agreement. Chapter 7: Wide and Lockdowns. Comprehensive survey of ML applications. Comprehensive survey of ML/DL algorithms. Comprehensive survey of COVID-19 ML/DL. Comparison of various regression techniques. Duration of statewide lockdowns in Maharashtra. Duration of statewide lockdowns in Tamil Nadu. Duration of statewide lockdowns in Odisha. Duration of statewide lockdowns in Punjab. Population density and confirmed COVID-19 cases of the selected stat. Chapter 8: Existing and Methods. Comparisons of the existing methods for brain tumor detection with T. Comparisons of the existing methods for analyzing the quality of SIR. Comparisons of the existing methods for data fusion with their limit. Chapter 9: Curve and Algorithm. Decision tree of J48 algorithm. ROC curve for J48 algorithm. Pseudocode for random forest algorithm. ROC curve for Rando. ROC curve for SVM algorithm. Workflow for linear regression. ROC curve for logistic regression. ROC curve for random forest algorithm. ROC curve for naive Bayes algorithm. ROC curve for KNN, NB, and RF. Chapter 10: Loss and Example. Example of lane marking detection. System design. Sample of a pre-processed image. Affected elements for each hyperparameter. Iterative process to fine-tune hyperparameters. Convolution neural network. Steering angle predictions. Tendency of predicted angles. Tendency of errors. Comparison of train loss versus test loss. Chapter 11: Analysis and Cases. Track check analysis system. Track check segregation analysis 1. Trend check analysis 2. Visualization chart of world COVID cases. Comparison of cases in hotspot countries. Death rate per million hotspot countries. Chapter 12: Predicted and Cases. Context of the work. The MVC architecture. The conceptual architecture. Illustration of SVR. The predicted cases before and after lockdown 1 in Maharashtra. The predicted cases before and after lockdown 2 in Maharashtra. The predicted cases before and after lockdown 1 in Tamil Nadu. The predicted cases before and after lockdown 2 in Tamil Nadu. The predicted cases before and after lockdown 1 in Odisha. The predicted cases before and after lockdown 2 in Odisha. The predicted cases before and after lockdown 1 in Punjab. The predicted cases before and after lockdown 2 in Punjab. Area chart to show the predicted cases before and after lockdown 1. Area chart to show the predicted cases before and after lockdown 2. Chapter 13: Algorithm and Value. Air Quality Prediction Architecture Methods. This layer is heart of dataset splitting. Algorithm for bagging. Structure for bagging. Algorithm for stacking. Structure for stacking. Algorithm for boosting. Structure for boosting. Sample data. Comparison of RMSE value. Comparison of MSE value. Comparison of MAE value. Prediction analysis of machine learning methods based on accuracy. Chapter 14, Model and Dataset. Block diagram of ML incorporated micro-application. Conceptual architecture. Best model for Case 1 sonar dataset. Model performance metrics for Case 1 sonar dataset. Best model for Case 2 liver patients dataset. Model performance metrics for Case 2 liver patients dataset. Best model for Case 3 automobile insurance claim dataset regress. Chapter 15, Facial and 8. Schematic depiction of the detection cascade. Alert system block diagram. 68 facial landmark coordinates from the iBug 300W database. The first two HA-like features. The 6 facial landmarks associated with the opening of an eye. Dataset used for building our model. 128 feature values have been extracted from S. Attention states. Attendances using facial recognition, Excel sheet and real-time X. Network speed. Text classification results. Chapter 16, Detection and Data. Anomaly detection system setup. Boxplot view to analyze the distribution of data attributes. Dimensionality reduction using PCA with 2 principal components. Scatter plots of A. Data with dimensionality reduction, B. PCAFT. Design of multilayer neural network model for outlier detection. SVM linear classifier. SVM nonlinear classifier with OPTI. Bayesian network in which each node is associated with a variable. A bar plot depicting the comparative analysis of adapted machine L. Chapter 17, Point and Time. Flowchart of genetic algorithm. Point addition. Point doubling. Flow diagram of the DCNN. Deep CNN model. Encryption time. Decryption time. Encryption performance. Decryption performance. Chapter 18, Aspect and Ratio. Facial landmark model. Eye aspect ratio positions and formula. Mouth aspect ratio position and formula. Eye aspect ratio at threshold. Eye aspect ratio below threshold value. Mouth aspect ratio below threshold value. Chapter 19, Data and Algorithm. Blockchain architecture. Types of blockchain. Traditional architecture of biometric recognition system. Various attacks. Various types of challenges in blockchain. Architecture of biometrics with blockchain. Part A medical applications. 1 Predictive models of Alzheimer's disease using machine learning algorithms and analysis. Carpegam G. 1 asterisk, Swatipriya M. 1, Charanya A. 1 and Murali Murugan 2 Department of Computer Science and Engineering, PSG College of Technology, Coimbatore, Tamil Nadu, India 2 Director of Engineering, Macy S., Georgia, USA. Alzheimer's is a neurodegenerative dementia that occurs in people aged above 65, and there is a rapid growth in the amount of people suffering from it. Almost 3 out of 4 AD cases are undiagnosed. This paper comes with the view of identifying a predictive machine learning model for Alzheimer's disease with the help of a minimally invasive blood-based biomarker. By comparing models of different algorithms of machine learning, we conclude that the model following the random forest algorithm has the highest efficiency in terms of predicting the positive AD cases with the highest AUC of the ROC curve. Machine learning, automated machine learning, Alzheimer's disease introduction. In the 1950s, many researchers attempted to build models that could interpret the world better than humans do. Then came the term machine learning, the concept by which the machine can learn and behave in the same way as humans do. Machine learning, ML, saw rapid developments in the late 1990s and in early 2000s and have found its applications across several different domains, including healthcare. The introduction of ML in healthcare has been a breakthrough in the industry, and it is still improving through the advancements in ML. Applications of ML models are used in the healthcare industry in several areas such as diagnosis of diseases, drug discovery and manufacturing, medical imaging diagnosis and outbreak predictions, etc. This paper focuses on analyzing the predictive ability of various ML algorithms and their models in the prediction of Alzheimer's disease, AD 469. AD is the most widely recognized type of neurodegenerative ailment leading to dementia that occurs mostly in individuals beyond the age of 65. A study says that only 1 out of 3 cases of AD are diagnosed across the world. As of now, the final diagnosis of Alzheimer's is only done through autopsy. It is one of the diseases whose prediction is difficult at an early stage, because it is often considered as normal symptoms of aging. 3. This difficulty in diagnosis may be the reason for the high ratio of undiagnosed cases to that of the diagnosed cases. So the need for effective and minimally invasive diagnostic models, diagnosis which doesn't involve severe break through the skin, is very much needed for early diagnosis by which we can avoid severe impairments. In the present study, we utilized the Merna transcriptomic dataset from the GEO repository and built models using different algorithms in the Waker platform and came up with the best predictive model by comparing the AUCs of the ROC curves of different models. Prediction of diseases using machine learning. For a while now there have been several applications of artificial intelligence that are prosperous in various fields. AI-assisted systems are utilized in healthcare, finance, education, and is considered as a boon with enhancement. Being a part of AI machine learning innovations have been able to meet the needs of the people, and its growth is unbounded. ML allows software applications to achieve a level of accuracy that can improve the current standards, too. In the healthcare industry, ML has been utilized to produce accurate predictions of a particular disease. This not only makes the work of healthcare professionals easier but also increases patient outcomes. ML has also been helpful in handling the data and records of patients and in developing new medical procedures. In some ways, these applications aim to make things a lot more efficient and easy for people to handle, including cost effectiveness. However, ML typically requires human intervention in various parts. This dependency on humans in order to achieve great performance sometimes becomes a hindrance. Thus, to reduce human interventions, save time and increase accuracy in results, an enhancement in machine learning technology is necessary. This programmed AI advancement is called automated machine learning, AutoML. Besides the fact that AutoML is an emerging innovative technology, it has been utilized in prediction and analysis of heart diseases, cancer, diabetes, and electronic healthcare (EHR) analysis. This chapter aims at exploring the ML algorithms and envisioning the best model that could help in predictions of Alzheimer's disease. As of late, researchers have been attempting to find biomarkers that indicate the presence of Alzheimer's in patients at an early stage in order to diminish or decline the advancement of the disease. There are various strategies that involve early diagnosis of Alzheimer's disease. Those include brain imaging, neuroimaging, functional imaging, molecular imaging, blood and urine tests, analysis of protein levels, cerebrospinal fluid, CSF, levels of tau and beta amyloid, and more. During this time, with remarkable improvement in the innovative field, the analytic investigation of Alzheimer's has also been improving. We now have reliable technologies in addition to the already existing clinical tests that can provide accurate diagnosis resulting in satisfying patient outcomes. AutoML has been used to successfully identify biomarkers that are minimally invasive. 7. This process promises combined computational efficiency and predictive performance. Materials and methods dataset. We used the openly accessible blood-based miRNA transcriptomic dataset from the Gene Expression Omnibus (GEO) repository in the process of building the predictive models. It comprises of data about the miRNA profiles in blood tests of 48 AD patients and 22 sound controls containing 506 features. 1. Tools. The comprehensive, open-source ML software Weka, which lets the users pre-process the dataset, apply diverse ML algorithms on data and analyze various outputs that was used throughout the process of building the models. Methods. 1. Data preprocessing. The data obtained from the GEO repository is converted into an ARF file in the experimenter application of Weka, and once the ARF file is ready, the Explorer application in the Weka GUI chooser is utilized for the rest of the processes. In this environment, we can explore our dataset by first going through the pre-processing process. Initially, the dataset is pre-processed by normalizing and then randomizing it. Since a raw dataset does not contain metrics that can be used for analysis, the values are kept within a scale that is applied for all numeric columns used in the model by normalizing it first. Normalization technique makes sure that our data produces smooth patterns where we can see a significant change in the model performance. It also helps in redundancy. Randomization is a technique that prevents a model from learning the sequence of training. Each point in the data implies independent change on the model without being biased by the same points before them. This is the first and most important step before sending the data to a model. 11, 12, 15, 17. Model development. Now that the dataset is pre-processed, it can be used to train a model. Here the method implemented is cross-validation 10-folds. It is a most preferred method since the model can train on numerous train test splits, offering clear and better signs of how the model will execute. This is done by training the full dataset. Then we use cross-validation 10-folds to test the model's ability of making predictions on new data. Visualization. Once the models are ready, the test summary will manifest the performance measures of each model on the dataset. There are several metrics, each with its own aim to depict the performance of each model. The area under the ROC curve metric gives the performance for classification models at various thresholds, indicating how useful the test is. The higher the value of area under the ROC value, the better a model is at differentiating between patients affected by the disease and the patients without the disease. Similarly, each metric has its own way of defining the performance of a model. In addition to these evaluation metrics, the visualization tool can also be used to visualize the results. 18, 19. Best model prediction. Following the results, predicting the best ML algorithm to distinguish between AD and healthy controls becomes easier. Comparing the area under the ROC curve, the random forest (RF) algorithm produced better results. 10, 13, 14, 16. ML algorithm and their results. 1. J48 tree. J48 algorithm is the Java execution of C4. 5 decision tree algorithm and C4. 5 thusly is an augmentation of ID3 algorithm. In this algorithm, the decision tree is built by splitting the tree from top root to the bottom leaf until it reaches a stage where it cannot be split further. The attribute with which the splitting decision is taken is called the splitting attribute, and it is chosen with the help of the information gain ratio. The attribute with the highest gain ratio at that level is chosen to split the tree further. To compute the data gain proportion, we utilize the idea of information gain and entropy. Entropy indirectly can be defined as how much variance the data has information entropy for a dataset with n classes, where p_i is the probability of randomly picking an element of class C. Information gain is used to measure how good the split is. Entropy is calculated for the splitted branches separately, and the entropy for the split is calculated. The difference between the entropy before split and after the split is referred to as information gain. Information gain ratio is the ratio of information gain to the split entropy. Information gain ratio equals information gain / split entropy pseudocode. Check for base cases for each attribute to find the information gain ratio from splitting on a let A_split be the attribute with the highest information gain ratio. Create a decision node that splits on A_split. Repeat the same on the sublists obtained by splitting on A_split and add those nodes as children of node. The decision tree for our classification is shown in A, and analysis via the J48 model produced a high AUC of which is shown in decision tree of J48 algorithm. ROC curve for J48 algorithm. Random forest. It is a ML technique that is used for solving both classification and regression problems. Among all the ML classification algorithms in use, random forest produces the highest accuracy rate. One of the major advantages of using this technique is that it reduces overfitting, eventually increasing the accuracy rate. Working of random forest algorithm, it resembles the ensemble learning process wherein multiple classifiers are combined to solve complex problems, and this increases the accuracy or the performance of the model. The larger the quantity of trees in a forest, the stronger the forest appears to be. Similarly, in the RF classifier, the greater the amount of trees, higher will be the accuracy rate or performance of the model. Random forest classifier contains a reasonable number of decision trees and produces prediction results of various subsets of the given dataset. When a new data point is fed into this phase, then based on the majority or taking the average value of the results, the classifier makes the final prediction. There are two main advantages of random forest algorithm. Since randomly selects subsets of features, the problem of overfitting is prevented. In comparison to decision trees where a set of rules or conditions are laid out once the training dataset is given as input and then prediction is made, random forest randomly selects features, builds a number of decision trees and then takes the average or majority prediction result. This gives us a high rate of accuracy. Explanation for the pseudocode of the random forest algorithm. This pseudocode works with a precondition that there is a training set S with features F and number of trees as B. A bootstrap sample from the training set S and S, I, denoting the ith bootstrap is selected draw each tree in the forest. Here we use bootstrap sampling technique because sampling is a process of selecting a subset of data from a collection of data, and this method involves drawing sample data repeatedly with replacement, since there is a chance that the data point taken from the sample can be repeated in the future also. At each node of the tree, we randomly select some of the features F, a number that is smaller than F, out of F, where F is the set of features. The best split of this F is used to split the nodes. The function randomizedTreeLearn, S, I, F, performs training of a decision tree on the bootstrap sample S, I, selecting F features randomly at each split. By narrowing down the set of features, we accelerate the learning of the tree. The below pseudocode is publicly available and is most commonly used for understanding the working of RF algorithm. Pseudocode for the algorithm precondition, a training set S, equals, x1, y1, xn, yn, features f, and number of trees in forest B. Analysis via RF model led to an AUC value of which is shown in pseudocode for random forest algorithm. ROC curve for random forest algorithm. Support vector machine, SVM. SVM is likewise one more well-known ML algorithm that can be executed for problems related to both classification and regression. Though it cannot perform well with a large dataset, it is most effective when in high-dimensional spaces. This algorithm is widely applied in biological and sciences fields. It can also be used for regression problems as well. Support vector machine is used for extreme cases like identification or classification of datasets and forms a decision boundary, also known as the hyperplane, surrounded by extreme data points. The data points nearest to the hyperplane are called support vectors and affect the position of the plane. SVM is a frontier which best sorts out two classes. There can be several decision boundaries for a given case, but choosing the best boundary becomes the challenge here for gaining accurate predictions. If there is no optimal decision boundary, there are high chances that new data could be misclassified or it could be incorrectly classified. This is where SVM comes into play. The algorithm basically suggests that only the support vectors are important and all the other training examples are ignorable. There are two categories of SVM. Firstly, the support vector regression, and the second is the support vector classifier. Here Waker executes John C. Platt's sequential minimal optimization (SMO) algorithm for training SVMs. SMO solves a challenge that is generally faced while training a SVM, and that is, it abstains from utilizing tedious mathematical quadratic programming (QP) optimization problems as solution. Also, it has been proved that SMO is much faster for training a huge size of data. It breaks the huge QP problem into a series of smaller QP problems and then solving it analytically. SMO performs well for large problems, and since it uses smallest QP problems which can be settled scientifically, its scaling and computation time is improved significantly. Analysis via SVM model produced an AUC value of which is shown in logistic regression. Logistic regression belongs to supervised ML classification algorithms that support binary classification, true or false. It is usually used when we want to predict the probability of a target value. It is widely used for disease detection. ROC curve for SVM algorithm. Logistic regression fits the data using an S-shaped sigmoid function, unlike linear regression where we attempt to fit the data in a line which can be used to predict unknown values. The curve tells the probability of the event. Logistic regression equation. Only when a decision threshold is taken into account, this regression can be used in classification. There are several factors which affect the threshold value, like precision and recall, which should be taken into account while deciding upon the threshold value. Analysis via RF model produced an AUC value of which is shown in nearest neighbor algorithm, KNN. The K-nearest neighbor method is a supervised machine learning approach that is ideal for classification tasks, while it may also be used for regression. It is one of the easiest ML algorithms that utilize a likeness determination strategy. That is, during the training, the KNN algorithm technique just gathers and stores data into categories, and when new data, test set, is inputted, it classifies the new data into a category that is more similar to the available categories. In simple words, it classifies a data or feature based on how its neighbors are classified. It is also named as lazy learning and non-parametric algorithm. There is no specific way to determine the k-value, that is, the number of neighbors. But usually in a binary classification problem, it is best to keep the k-value as an odd number. It is also a good practice to use large numbers for k-value but not too large, otherwise a smaller number of data will be beat by other categories. Gives the percentage of the total dataset which were correctly and incorrectly classified for different ML algorithms. Algorithm correctly classified, %. Incorrectly classified, %. Chapter 20, Naive Bayes. The steps to understand KNN algorithm is given below. Initially load the dataset for which prediction is to be made, input a value for k, iterate from 1 to total number of features data points in the dataset, compute the distance between each row of the training set and the test set. The Euclidean distance technique was used to calculate this distance. Furthermore, based on the distance values, the estimated distances are ordered in increasing order. In addition, the top k rows of the sorted array are taken. The most often occurring class from these rows is chosen in this stage. Return the anticipated class at the end. Workflow for linear regression. ROC curve for logistic regression algorithm. ROC curve for random forest algorithm. These are the basic steps for understanding the working of KNN algorithms in machine learning. Analysis via KNN model produced an AUC value of which is shown in Naive Bayes machine learning algorithm that is considered as the simplest yet powerful algorithm for classification problems. As the name suggests, the algorithm works based on the Bayes theorem in mathematics, which is used for calculating conditional probabilities, thus being a probabilistic machine learning algorithm. Thus, it is a given that naive Bayes work or classify based on an assumption that each feature in a dataset is conditionally independent, that is, each feature is unrelated to each other. Given below is the formula for Bayes' theorem. The above formula calculates the conditional probability of a class. In general, P(H)E is posterior probability, P(H) is considered as prior probability, P(EH) as likelihood, and P(E) as predictor. Thus the above Bayes formula can also be rewritten as, in terms of disease prediction, the formula above is used to determine the likelihood that a patient has AD based on whether the test is positive or negative. There are three main measures that give a better understanding of prediction of the disease. This includes base rate, sensitivity, and specificity. The sensitivity measure will reveal the percentage of persons who are genuinely suffering from Alzheimer's disease and have been diagnosed as such. The percentage of those who do not have Alzheimer's disease and are tested to be healthy patients will be used to determine specificity. The percentage of persons with Alzheimer's disease will be represented by the measure S-base rate. All these measures could be conveniently calculated using Waker S features that includes confusion matrix, test summary, and from the threshold curve for AD patients, thus making the prediction process accurate with given dataset and information. The Bayes theorem is simplified in the naive Bayes classifier. The Bayes theorem in general assumes that input data is dependent on all other data, creating a complexity. Thus in the naive Bayes classifier, the probability of class for each input data is calculated separately and multiply the resultant values together. Analysis via naive Bayes model produced an AUC value of which is shown in ROC curve for naive Bayes algorithm. Finding the best algorithm using experimenter application. In order to find the best algorithm with highest accuracy for our dataset, we utilized the experimenter application provided by the Waker GUI. It is a powerful tool that is designed to analyze datasets against all the ML algorithms, provided it satisfies the criteria appropriate for that algorithm. Summarized table for all metrics obtained from all the models. Algorithm. Chapter 21. Add. For example, certain algorithms do not support binary classes like simple linear regression. In such an instance, the tool will throw an error and does complete the run analysis process. After making the required changes, Waker can now analyze the dataset to see how accurate each algorithm works on our dataset. For this, we set the test base to ranking and the comparison field to area under ROC curve. After running the test, we can see that the random forest method is the best for our dataset, with the greatest accuracy rate from. In order to display the values of area under ROC curve, we can set the comparison field to area under ROC and test base to any algorithm. Once the test is performed, we can evidently see that compared to all the ML algorithms, random forest produced better performance results. We choose AUC, ROC curve as a factor to decide which algorithm is best and tabulated it in. AUC-ROC is the best metric when it comes to ranking predictions and also considering both classes equally. Conclusion: we evaluated mRNAs from the blood samples of persons with Alzheimer's disease and healthy controls to find the best machine learning algorithm that might be used to diagnose and forecast the disease. Using the same dataset, we trained models on various ML algorithms. With machine learning, prediction of diseases has now become a time-saving process and promises accurate diagnostic measures. All of these analyses revealed an accuracy rate of 2 from, indicating that mRNA biosignatures could be employed as a biomarker for Alzheimer's disease prediction. In the final analysis, we can see that the KNN-ML model indicates an excellent area under ROC value of, which is an acceptable prediction rate for identifying AD disease. Though KNN Model S prediction was excellent, analysis via RF model illustrated an outstanding area under ROC value of, while other algorithms indicated only a fair accuracy rate and naive Bayes with a poor accuracy rate of. With additional technological developments, we may be able to forecast Alzheimer's disease at an earlier stage, thereby slowing the course of symptoms and resulting in happier patients. The comparison of the algorithms that depicted the best area under ROC value. ROC curve for KNN, NB, and RF. Future scope: the present study comes with the objective of analyzing how the emerging technology AutoML, automated machine learning, can be useful in building precise predictive models for identifying diseases using diagnostic clinical data. ML has been infiltrating every facet of our life, and its good influence has been perplexing. Automated machine learning, AutoML, technology can be used to speed up this ML technology and apply it into a variety of real-world settings. In healthcare, AutoML can make the workload of doctors and other healthcare specialists easier. The fundamental goal of AutoML is to make the technology accessible to the general public rather than just a select few. With AutoML technology comes an opportunity to improve healthcare with less human interventions involved, as most of the processes are automated. With this aim, we survey relevant ML and AutoML papers and analyze the role it can play in the field of healthcare. 2 bounding box region-based segmentation of COVID-19 X-ray images by thresholding and clustering. Kavitha S. and Hannah Inbarani, Department of Computer Science, Periyar University, Salem, India. Image segmentation is used to decrease the complication of an image for further processing, analysis and visualization. This work presents the bounding box-based segmentation methods through thresholding, k-means, and fuzzy k-means clustering to segment the COVID-19 chest X-ray images as it involves simple calculations and fast operation. Bounding box is generated over the image to locate the object of interest on an image. Before applying these methods, the images are histogram equalized using Clay-Hay to improve the quality of a foggy image with the limited increase in the contrast. The results are evaluated using intersection over union, IOU, and mean pixel accuracy, MPA, with the segmented and the ground truth image. contrast-limited adaptive histogram equalization, Clay-Hay, bounding box, thresholding, k-means clustering, fuzzy k-means, mean pixel accuracy, MPA, intersection over union, IOU, introduction. Coronavirus, COVID-19, is one of the most abundantly spread viruses in the world, affecting more than 200 countries, causing an overwhelming epidemic. As the virus is causing more deaths, it has increased pressure on health organizations to save the affected patients. Hence, it is necessary to detect the virus in a patient as early as possible to provide efficient and accurate treatment. There are many applications of image segmentation, such as medical image processing, face recognition, satellite images, etc. Currently, medical imaging such as chest X-rays and chest CT scans can be used to diagnose the disease efficiently. As the manual processing takes a lot of time and the dedicated staff to detect the disease from the medical images, it is necessary to create an automated system on medical image techniques to find the disease with higher accuracy and less time. 2. Image segmentation is one of the essential steps in medical image processing for image analysis and recognition. It is used to divide the image into multiple segments from which any useful information such as color, intensity, and texture can be obtained. 3. Though there are several segmentation algorithms used by the several researchers, this paper analyses region-based segmentation such as thresholding and clustering using k-means, fuzzy k-means on COVID X-ray images for segmentation, since these methods involve simple computation and speed. Commonly, the X-ray images are low contrast. 4. Therefore, the image contrast is increased using adaptive histogram equalization before segmentation so that the image is segmented very effectively for further processing. 5. Threshold segmentation is one of the simplest and widely used region-based segmentation method, which sets the threshold value. The pixel values falling below or above that threshold can be classified accordingly as an object or the background. 6. The next type of segmentation method, called clustering, that divides the image into clusters whose elements have similar characteristics in the elements in the same cluster compared to the elements in the different clusters. 7. There are several clustering methods have been proposed and applied in image segmentation. K-means, proposed by Pengfei Shan, 8, is an unsupervised algorithm that divides the image into K clusters to segment the image into different clusters. The main aim of this work is to segment the image using these methods after generating the bounding box and enhancing the contrast. The next section presents the related work. Section explain the data set used for analysis and proposed methodology respectively. Section discusses the findings and at the end, the conclusion is presented. Literature review. So for various research works have been done for segmenting the different types of images which are shown in segmentation of images using various techniques. Authors' techniques result Maria Fayez, Sohar Safwat et al. 9. K-means and 2D wavelet transform with K-means are implemented. 2D wavelet transform with K-means clustering achieved better performance. Namarikpam Dhanachandra et al. 10. K-means and subtractive clustering. The proposed algorithm has achieved better segmentation. Alan Jose, S. Ravi and M. Sambath. 11. K-means and fuzzy C-means. Region of interest and the size of the tumor are found from the resultant segmented image. Ajala Funmalola A. et al. 12. Fuzzy K-C-means clustering is applied on brain MRI images. Better time utilization. Senthil Kumaran N. and Vaithegi S. 13. Local thresholding algorithm, Niblack and Sauvala. The result of the Niblack algorithm is good compared with the Sauvala algorithm. Jobin Christ et al. 14. Silhouette method, spatial FCM, fuzzy C-means, HMR FFCM, They concluded that the HMRF-FCM converge fast and gives less error and better accuracy. Silhouette method finds the correct structure and spatial FCM improves the segmentation results. Kaur and J. Rani, 24. Different histogram equalization methods are used. Clay-Hay is better than LHE, local histogram equalization, as it consumes more time. Huntoro Wang and Xiaolong Su, 8. K-means and outliers detection method. It has more accuracy but for large datasets it takes more time. Yadav et al., 17. Clay-Hay is used to increase the image quality. The result of the proposed algorithm shows the better quality video. Amy Salihai Abdul et al., 20. Partial contrast stretching and K-means clustering. Accuracy % F-scored Dhanalakshmi, K, and H. Hannah in Bharani, 25. Fuzzy soft rough K-means clustering. Proposed method shows good efficiency. Dataset used this study uses 2 COVID images and the associated ground truth images for evaluation. The images are with the size 237, 233, 3, and 227, 239, 3. Downloaded from the link https://www. ResearchGate. Net figure the COVID-19 sample CXR images their corresponding ground truth segment. Proposed method in this work, we proposed a segmentation model in which Clay-Hay and the bounding box representation are combined with the thresholding, K-means, and fuzzy K-means clustering to segment the COVID-19 X-ray images. The proposed model has the following steps and it is represented in. Read the image. Apply the contrast limited histogram equalization. Generate bounding box over the histogram equalized image. Then, segment the resultant image using threshold-based segmentation and clustering techniques. Resultant images of the previous step are compared with the ground truth images through mean pixel accuracy and IOU, intersection over union. Proposed method. Histogram equalization. Histogram equalization tries to flatten the histogram to adjust the contrast or brightness of an image to create better quality image. This method helps to produce the better views for X-ray images. 15. The modified part of histogram equalization called adaptive histogram equalization, ADE, performs image enhancement on a particular region and adjusts the contrast based on the nearby pixels. 16. Clay-Hay is an improved method of AHE in which the image enhancement is applied on small regions of an image to improve the contrast. 17. It limits the contrast stretch to avoid over-amplification of the contrast. In this work, the sample image is enhanced through Clay-Hay with the clip limit value fixed as to limit the contrast stretch. It is shown in the contrast limited adaptive histogram equalization. Threshold-based segmentation. In threshold-based segmentation, the pixel values which are under the threshold or the values which are above the threshold is considered as an object or background. It can be stated as, in the above equation, the threshold value point t has the coordinates p and q, f, p, q, is the gray level and s, x, y, is some local property. 18. The resultant image is obtained as r, p, q, which is stated as, in this work, local thresholding is used in which multiple threshold veils are set to segment the X-ray image into different classes. The first threshold value is found by calculating the mean of the pixel values of an entire image. K-means clustering. K-means clustering divides the given dataset into K predefined distinct non-overlapping clusters. It is an unsupervised machine learning algorithm. Each value from the dataset belongs to only one group. For each data point, the squared distance is obtained among the data points and the cluster centroid. Based on the distance value the cluster is found for each data point, 19. The steps of k-means clustering, 20, consist of total number of clusters k and the centroid is specified. For each pixel and the centroid, the Euclidean distance d is calculated as, based on the distance value d, all the pixels are allotted to the nearest cluster. Calculate the new position of center once all the pixels are assigned by. All the above steps are continued till the error value is satisfied. Fuzzy k-means clustering. Fuzzy k-means is a widely used soft clustering method for MAGE segmentation. 21. In fuzzy clustering, the data elements are assigned with membership levels. Based on these levels, the data elements are allotted to one or more clusters. This technique is used in the applications where there is no crisp boundary between clusters. The objective function of FCM, 22, is represented as, where U is the membership matrix and UIN denotes the degree of membership of pixel in nth position and the ith cluster. DIN is the Euclidean distance amongst pixel data and the ith cluster. Experimental analysis results of histogram equalization. The given two COVID-19 X-ray images are histogram equalized using Clay-Hay with the clip limit value fixed as. It is shown in sample. Histogram of image *1 after histogram equalization. Histogram of after histogram equalization. Sample. Histogram of after histogram equalization. Histogram of after histogram equalization. From it is shown that the contrast of the given X-ray images are increased and is given as input to the segmentation models for further analysis. Findings of bounding box segmentation. The segmented images after applying threshold-based segmentation, k-means, and fuzzy k-means clustering on the images extracted with bounding box. Evaluation metrics. A. Mean pixel accuracy. Pixel accuracy computes the proportion of the number of correctly categorized pixels among the overall pixels. MPA is an enhanced pixel accuracy where it calculates the correct pixels per class to find the average of all classes. It is given, 23, as segmented images of an image *2. 1. Image with bounding box. Thresholding. K-means. Fuzzy k-means. 6. With bounding box. Thresholding. K-means. Fuzzy k-means. Where k+1 is the total classes and pi represents the number of true positives and pij denotes the false negatives. Intersection over union, IOU, it is an evaluation metric to measure the overlap between the intersection and union of two bounding boxes such as the predicted segmentation and the ground truth. It divides the intersection of predicted and ground truth by the union of predicted and the ground truth image. The lower value of IOU indicates that the prediction is incorrect. It is formulated, 23, as C. Accuracy results of segmentation algorithms. All the segmented images which are generated without bounding box are compared with the ground truth images using the metrics such as MPA and IOU for evaluation, and the accuracy values are specified in the MPA and IOU score of the segmented images generated for the images with bounding box and the ground truth images. From the AND, it is shown that the IOU score of all the methods is high for the images generated with bounding box compared to the IOU value of images without bounding box, and the threshold-based segmentation gives better accuracy than the k-means and fuzzy k-means method. MPA and IOU scores of different segmentation algorithms. Evaluation metrics. Images without bounding box segmentation algorithms. Threshold-based segmentation. K-means clustering. Fuzzy k-means clustering. Mean pixel accuracy. IOU MPA and IOU scores of different segmentation algorithms. Evaluation metrics: images, bounding box segmentation algorithms, threshold-based segmentation, k-means clustering, fuzzy k-means clustering, mean pixel accuracy. IOU conclusion: in this chapter, we have generated bounding box over the images and analyzed the images through the segmentation technique such as region-based segmentation using thresholding, k-means, and fuzzy k-means clustering to segment the COVID X-ray images. The image contrast is increased using Clay to create a better quality image before the segmentation. Generating bounding box over the image helps to locate the object of interest and to reduce the number of features such a way it increases the segmentation accuracy. The results of the segmentation methods are evaluated by matching the segmented image with the ground truth image using MPA and IOU. In the future work, deep learning-based segmentation will be applied on the COVID-19 images to obtain the more accurate segmentation. 3. Steering angle prediction for autonomous vehicles using deep learning model with optimized hyperparameters. Benisha J. 1 *, Vinod Kumar B. 2. Karthikeyan T. 3 and Syed Khoja Mohideen 3-1 Department of Computer Science and Engineering, PSG College of Technology, Coimbatore, India 2 Department of Information and Technology, PSG College of Technology, Coimbatore, India 3 Department of Information Technology, University of Technology and Applied Sciences Salalah, Oman. Autonomous vehicles will optimize our transportation infrastructure and could in the long run improve our lifestyles. Machine learning has recently advanced, allowing us to get closer to making this technology a reality. The capability of deep learning algorithms is used in the proposed study to construct a model that can anticipate steering angles nearly identical to how a human would manage a car's steering wheel. This was accomplished by training a 9-layer deep neural network. Optimization of hyperparameters of neural network models is performed for better results. The model was trained using a small dataset of less than 30 minutes of driving data, resulting in a root mean squared error of on the testing dataset, far above the benchmark of. Finally, this score indicated deep learning model's capacity to execute in a human-like manner with only a minimal amount of training. Self-driving cars, deep learning, steering angle, CNN, genetic algorithm introduction. One of the most significant technological problems of this decade has been the development of autonomous automobiles, which has a significant impact on our society by preventing car accidents, reducing traffic, maximizing fuel efficiency, and lowering vehicle costs. Autonomous automobiles can also save time traveling to work and minimize car ownership costs by moving to an on-demand mode of operation. Due to the deployment of deep learning algorithms and techniques, such as convolutional neural networks, CNNs, there have been several notable developments in the field of autonomous cars in recent years. Pattern recognition, 1, has been revolutionized by CNNs, 2. Until CNNs became extensively used, most pattern recognition applications had feature extraction stage manually designed, which is then preceded by a classifier. CNNs are revolutionary because they automatically learn characteristics from training samples. Applications that require identification of images demand an efficient technique like CNN, as they catch the two-dimensional element of the image. Furthermore, by scanning a full image with convolution kernels, only a few parameters must be acquired while comparing with the overall tasks. CNNs which possess learnt characteristics have been widely used for over 2 decades. 3. CNN's popularity has skyrocketed over the decades as a result of significant advancements. To begin with, huge, labeled datasets have been accessible for training, testing, and validation. Secondly, to dramatically speed up training and prediction, CNN models are in graphics processing units. The suggested method displays the capacity to control a car's steering just by processing visual frames acquired using the power of CNNs. Current autonomous steering solutions necessitate an explicit dissection of challenges, like detecting marks in a lane. The main purpose of this research lies in the avoidance of recognition of objects picked by humans like lane dividers, marks in the lane or another car. This research also focuses on the creation of rules by observing these qualities. The main goal is to leverage data from Udacity to create a framework which determines the angle of a vehicle's steering wheel with a little amount of training, 30 minutes of driving data. The model receives car's front view images and produces the angle of the steering wheel. This problem involves predictions of continuous data. End-to-end solutions, in which a single network receives raw input, camera footage, and generates a direct steering order, are seen to be the highlight of current autonomous vehicle technology, and are expected to make up the first wave of self-driving automobiles on roads and highways. We can avoid a lot of the complexity that comes with manually selecting features to detect and substantially lower the expense of getting an autonomous vehicle on the road by bypassing LiDAR-based solutions by letting the car figure out how to interpret photos on its own. Example of lane marking detection. The paper is structured as follows. In literature review, several research papers are discussed. In section 3, the proposed system design is illustrated. Its components and working methodologies are also discussed in detail. Section is a discussion of the experimental results relating to the proposed system. The paper ends with conclusions and ideas for future work in section. Literature review in 1. The standard design of an autonomous system is proposed. Furthermore, an in-depth study of an autonomous system called the Intelligent Autonomous Robotics Automobile is also presented. A number of platforms which do research on autonomous vehicles were developed by many technology firms and are proposed and published as well. In 2. A self-driving car prototype which is based on monocular vision and employs neural networks on Raspberry Pi is proposed. In recent years, it has been demonstrated that convolutional neural networks, CNNs, outperform other techniques in a variety of perception and control tasks. The capability of learning thousands of characteristics from a big volume of labeled information is one of the core aspects behind these amazing outcomes. In 2. A deep neural network is used to find an approach that inputs raw data and outputs steering wheel angle prediction. 3. Proposed a study to see if low-utilization rural public transportation lines may be substituted with autonomy systems on demand. A cost and service level comparison was made between current transit systems and potential transit systems that are available on demand. Another analysis, focusing on operational considerations, is proposed, employing a simulated technique wherein the robot taxis are controlled in a road system, considering congestion impacts. The findings show that for rural locations, a central controlled transit system that is available on demand will be an appealing choice. An algorithm that is exclusively reliant on visual or camera input is proposed by 4. A powerful lane recognition technique for autonomous cars is presented utilizing modern computer vision techniques. Simulation results in various scenarios are shown to prove the efficiency of the suggested line detecting technique when compared to the standard techniques. In real-world driving video simulations, YOLO, which stands for You Only Look Once, is a CNN algorithm used for detecting objects. 5. The computations are performed by the NVIDIA GTX 1070, which has a RAM of 8 GB. The paper demonstrates the strategies proposed for lane guidance and autonomous vehicle environment. 6. Proposed a caching technique in autonomous cars, which is dependent on passenger characteristics gathered through deep learning. The following suggestions were also made. At first, deep learning models for content prediction must be cached. Secondly, a communication technique is required for collecting and caching infotainment content. An approach for light detection and ranging, LiDAR, and camera fusion is presented by 7, which could be suited for executing with time constraints in self-driving cars. This approach is based on the clustering algorithm. 8. Proposed a way for using reinforcement learning, RL, under 2 conditions. 1. RL works in combination with a baseline rule-based driving policy, and 2. Only when the rule-based method appears to be failing and the RL policy's confidence is high, the RL gets involved. Their motivation was to apply an inadequately trained RL policy to improve audiovisual AV performance consistently. The suggested strategy outperforms both the pure RL policy and the baseline rule-based policy in simulations. 9. Proposed the following aspects: a view on autonomous vehicles with an emphasis on perception, how self-driving cars will be affected technically and commercially by government policy, and how cloud infrastructure will perform an important role in development. 10. Also proposed a learning strategy for calculating the best steering angle for keeping the car in its lane. With the human driving data as input, the model can steer the automobile and stays in its lane after training. 11. Explores a tracking system for trajectories. The steering angle of the vehicle's front wheel is computed using a predictive controller with tire cornering angle and road traction limitations. The objective of 12 is to use a broad survey to act as a bridge between neural networks and autonomous cars. Feudal steering, the method proposed by 13, is based on current hierarchical learning, HRL, work and consists of a manager and a worker network. The networks function on separate temporal scales. The task is divided into management and worker subnetworks via feudal learning. In driving, temporal abstraction allows for more complicated primitives than a single time instance of the steering angle. Quantitative arguments and qualitative arguments of how cameras can reliably predict the angle of the steering wheel even when traditional cameras fail is proposed in 14, for example, during fast motion and difficult lighting circumstances. Finally, the benefits of utilizing transfer learning from conventional to event-based vision are highlighted, and it is demonstrated. Methodology architecture: 3 main cameras, one at the left, one at the right and one at the center, record the surroundings, and the output is sent to the random shift and rotation part, wherein the images are randomly rotated in clockwise direction by a given number of degrees, after which the output is passed to the hyperparameter tuning section, where an optimal combination of hyperparameters are selected for the learning algorithm. The next stage involves the CNN, which takes the input image and predicts the steering wheel angle. System design. Data Udacity's Challenge No. 2 dataset was used to train this model, which is based on driving data from San Mateo, CA to Half Moon Bay, CA, curvy and highway driving. This collection contains image frames collected by a set of onboard cameras, each of which is linked to a certain steering angle and timestamp. Udacity excluded stationary segments and lane shifts from the dataset. Only the middle images were chosen, despite the fact that the imagery originated from 3 distinct cameras: left, center, and right. There are 6 pieces to the Challenge No. 2 dataset. As needed by Udacity's Challenge No. 2, parts 1, 2, 5, and 6 were used for training, while parts 4 and 3 were utilized for validation and testing respectively. Data preprocessing. The objective of data preprocessing stage is to process data from raw input video into an understandable format. A preprocessing phase, 7, is performed on data used for training and inference, in which various inputs are scaled to the same dimensions and stacked into batches. Although inputting non-preprocessed video and allowing the neural network to learn features is applicable, but emphasizing on processed video will accelerate the process of training. Hence, video processing is performed first. Video processing is the process of breaking down a video into individual frames. The following are the pre-processing steps that were used. The 640/480 pixels raw images in the dataset are scaled to 256/192 pixels. Because the RGB colors on the images do not provide relevant information to help estimate steering angles, the images were converted to grayscale. 2 successive difference images were used and computed lag 1 differences between image frames. For example, at time t, 1, 1, 2, is given as an input, where x denotes the grayscale image. To anticipate the current steering angle, no future frames were used. All of these stages contribute to reducing the size of the data and magnifying more relevant data, allowing the model to run faster and more precisely. Every image in the training, validation, and test subsets was subjected to data preprocessing, depicts an image after it has been preprocessed. As can be seen, RGB colors have been eliminated, leaving only the borders visible. These edges aid in the Model S recognition of patterns such as street lanes and other cars. Sample of a pre-processed image. Hyperparameter optimization. In any deep learning algorithm, the hyperparameters affect certain elements such as our batch size, filter size, and learning rate. 4, which in turn affects the accuracy of the algorithm. These elements are either established by external influence or by a developer's background experience. Rather than using conventional methods and probabilities, genetic algorithms are the ideal choice for optimizing hyperparameters. The following steps are performed in order to solve the issue of hyperparameter. Affected elements for each hyperparameter. Generate a population of numerous NNS. Allocate hyperparameters to each NN at random, within a range. For a certain number of iterations, the following steps are performed, training all the NNs at the same time or one at a time. Compute their training costs once the training is completed. Determine each NNS fitness based on its cost. Determine the maximum fitness of the population, essential for step 5. Choose 2 NNs based on their fitness as determined by a probability scheme. Crossover is performed over the genes of the 2 NNs. The obtained child NN will have properties of both NNS. Mutation is performed over the genes of the child NN to introduce some randomness to the algorithm. For the number of NNS of the population, repeat steps 5 to 7. Save the obtained children in a new population and allocate the obtained population to the old population S variable. After performing all of the processes above, the algorithm will produce a population comprising a NN with the optimal hyperparameters. Of all the population, the obtained population will have the fittest NN. Depicts the iterative process to fine-tune hyperparameters using genetic algorithms. The hyperparameters, batch size, epoch size, filter size, and learning rate are considered. 100, 30, 5 are the hyperparameters obtained after optimization by the genetic algorithm. Iterative process to fine-tune hyperparameters. Neural network deep learning refers to the use of neural networks for machine learning because of its ability to extract deeper information patterns from provided data by replicating how real neurons behave. CNN has proved its efficiency in classification and recognition of images. CNNs are used to extract features from images by lowering their dimensionality. Through a succession of convolutions, the CNN design decreases the dimensionality of an input image until it provides a single output at the end. Convolutional layers operate by filtering over small sections of an image. A convolutional layer requires two primary parameters to do this: kernel and stride. The kernel is the size, in pixels, through which each convolution will filter, while the stride is the amount of pixels that are shifted each time our filter is moved. The result is nearly alike as the input size when stride is set to 1. It is about half the size with a stride of 2. The architecture of the network. 6 has 9 layers, comprising of 5 convolutional and 4 fully connected layers. The convolutional layers were chosen based on the results of a series of trials, having each layer configured differently. Convolution neural network. In the network, the first 3 layers utilized a 2x2 stride with a kernel size of 5x5 kernel. The remaining layers are non-strided and use a kernel of size 3x3. 3 fully connected layers follow the network's 5 convolutional layers, leading to an output control value that is the inverse turning radius. Training. In order to reduce the difference between the values of the input, human-driven command, and output, the steering wheel angle prediction, the weights of a neural network must be trained. Epochs are used to train deep neural networks. Each epoch trains the Model S weights by passing batches of pre-processed images through it, as well as providing values for training and validation loss. Following training, the weights with the lowest validation loss are fed into the model, which predicts the test dataset's output. The dataset consists of a 30 frame per second, which is a 25-minute video of an actual car driving, around 45,000 images. The weights were trained in order to reduce the mean squared error, MSE, between the input and output. The dataset is split in 2 halves in a temporal order, with the first 80% used for training and the second 20% for testing. Experiment and results. The structure of this model comprises 9 layers with a total of 444,819 parameters, which implies that there are over 400,000 parameters that can be tweaked for each image that travels through the neural network in order to forecast steering angle. Curves, street lanes, cars, and other components may be identified using some of these parameters. Image augmentation was used to pre-process all of the input data, allowing the model to perform better and have an RMSE of less than. The data that machine learning models are fed is one of the most essential factors. We went a step further in this example, cleaning the dataset by deleting segments that remained constant for extended periods of time. Because of the filtering, the model was able to overfit more slowly, resulting in more accurate predictions and an RMSE of less than. Because of this, the model was able to achieve a validation loss of during training, resulting in a final RMSE of. As a result, the model accurately predicted steering angles with an RMSE of. Benchmark. Udacity provides a benchmark for researchers to measure their Model S performance in order to make the review process easier. For comparison, an example file with an RMSE of has 0 for every steering forecast. This implies that a good prediction model should have an RMSE of less than. An RMSE of is used as a benchmark for this problem. Although the model does not forecast angles perfectly, its RMSE of indicates that it performs admirably with a very small difference when compared to human-controlled steering, shows how the steering angle predictions can be visualized in a simulator-like format in a video. Steering angle predictions. Tendency of predicted angles. Tendency of errors. Comparison of train loss versus test loss. And show the patterns for both our Model S predictions and the errors resulting from those predictions, providing a more detailed picture of the findings. A positive trend in the predictions, indicating that if the real angles increase, the anticipated angles will increase as well, and vice versa. an almost neutral tendency for errors between predictions and real angles, implying that the error rate remains roughly constant regardless of whether the real angles grow or decrease. A comparison of train loss, blue, versus test loss, green. The forecasts can be observed to be very close to the real angles, with only a minor variance on larger angles. The comparison of predicted versus actual steering angle predictions. Comparison of predicted angle versus actual steering angle. Predicted angle, actual steering angle. Dash, 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 dash. Conclusion: this model shows that CNNs have the capability to learn the road without manual decomposition. The best results were achieved when the hyperparameters of CNN were optimized using genetic algorithms. With a minimal size of driving data, 30 minutes, the model learnt to steer a car like a human. From a sparse training signal, steering alone, the CNN is able to learn relevant road features. During training, for example, the system learnt to discern the road layouts without using tagged labels. Even while this model works well, there are several modifications that can be made to make it even better. Further work is required to enhance the network's reliability for affirmation, and improve the visualization of the network's internal processing stages by including depth features and information from LiDAR. Training using a variety of road conditions, such as road type and weather, may enable the model to learn to drive over a wider range of terrains. The model may be able to reduce the error for big steering angles if it is trained on a larger dataset with a wider range of curves. For review of classification and feature selection methods for genome-wide association SNP for breast cancer, L. Sujithra 1 * and A. Kuntha 21 CSEDR. Institute of Technology, Coimbatore, India 2 Coimbatore Institute of Technology, Coimbatore, India. Cancer is a complicated disease with many molecular changes driven by hereditary, environmental, and lifestyle factors. Cancer cells develop abnormalities that alter the cell's normal development, proliferation, and death cycle. Breast cancer remains the commonest analyzed cancer among women and the main cause of cancer-related deaths. Selection and identification of single nucleotide polymorphisms, SNPs, remain most significant assessment for genome-wide association studies, GWAS, related to breast cancer. Nevertheless, at the domain to detecting SNP and classification of healthy patient, several significant challenges remain. The greatest difficulty is the problem of dimensionality, as the total amount of observations is significantly less than the total amount of SNPs, and the healthy patient data quantity also differ. Because of these difficulties, selecting and classifying features is extremely challenging. Machine learning, ML, is a revolutionary method that is ideally situated to uncover the unseen biological interactions used for enhanced breast cancer finding and diagnosis. This review goal is to determine the best effective approach of analyzing SNP data by combining several feature selection, FS, and classification methods. This paper describes genome-wide prediction analysis to construct methods that predict whether or not by a latest proceeding can diagnose the breast cancer dependent on the SNP set. It also gives an overview of FS and techniques of machine learning used to predict breast cancer. Latest FS and machine learning application advancements are highlighted, with descriptions of how these techniques can lead to enhanced disease identification and the incorporation of genetic features into future customized healthcare. Single nucleotide polymorphisms, SNPs, deoxyribonucleic acid, DNA, genome-wide association studies, GWAS, introduction. Complex diseases frequently lack a clear biological inheritance pattern at the level of population. Specific elements can't cause for disease to appear. Natural life, scientific experimentation, and research collections can all be used to build a biological data knowledge base. Where species-specific information is available, classical organism collections are useful, as it aids in new discoveries. 1. Numerous biological research investigations have been piloted, resulting in enormous genetic data resources. These information sources, it is frequently stated, are not yet properly exploited. 2. These sources of data also provide statistical issues. For example, the family-wise error rate, FWER, shows at least single incorrect discovery in several tests, which is known as to generate major false positive issues. 3. FWER rises as the number of marker candidates grows. From the growth exposed, that issue of computing slant is substantial in genomic data, therefore, the size of input file is the same, but the processing time for variant calling is quite differs. A variant in a single nucleotide that resides at an exact locus at the genome that is appear in a population of a residence to a significant degree. 4.6. It is necessary on the way to examine disease-associated SNPs used to help expose the genetic basis of complex hereditary disease using genome-wide genotyping of SNPs in genome of humans. 7. Single nucleotide polymorphism differences in base pairs of DNA and SNP profiles have remained known for genome-wide association studies, GWAS, area to define a wide range of disorders in it. The quantity of SNP is generally higher than quantity of thing. That is the heart of artificial intelligence for sustainable applications. If it helped, a quick subscribe keeps more summaries coming. So how do data and image connect? That is exactly where we started. Go back to the top and watch it click into place.